Great, thank you. Can everyone hear me? Is that okay? Yeah, okay. So.
Sorry, could you move a little further to your right, otherwise.
Oh, the mic, yeah, okay. Is that better? Awesome. Okay, so like Joel just mentioned, so I'll be telling you about categorical boson, the categorical boson fermion correspondence, and Bernstein operators. But before that, I want to just mention very briefly what the motivation for this is. So in the 90s, Frankel conjectured that we could categorify conformal field theory. And VOAs, right? So vertex operator algebras. And as a starting point, he said, well, why don't we begin by categorifying the boson-fermion correspondence? And the associated vertex operators. However, this problem kind of lay dormant for many, many years until in 2011. In 2011, we had the work of Caudis and Licata, where they realized categorical vertex operators as functors acting on two representations of Heisenberg categories, right? So they realized categorical vertex operators as functors on Heisenberg categories. Great. So then motivated by this progress, then in, I think it was 2013, we had Caudis and Sussin conjectured a categorical boson fermion correspondence. And that's exactly what I want to talk about today. So it's this. This is the motivation, and then in order to do that, I want you to keep a certain picture in mind, which, yeah, let's just do it here. So the big picture to keep in mind is the following, right? So we're going to have some sort of symmetric functions. We're going to call it Fock space, whatever you want to think of. And the idea is that on the ring of symmetric functions, we're going to have two actions. We're going to have the action of a Heisenberg algebra. We're going to have an action of a Clifford algebra. And there's a way of relating these two actions, right? And that action, or that relation, is precisely known as the boson-fermion correspondence. So this is the big picture that I want you to keep in mind, which is what we're aiming to categorify, right? It's basically, how can we lift symmetric functions, the Heisenberg algebra, the Clifford algebra, and this boson-fermion correspondence to some sort of categorical analog. Okay, great. So now, let's actually get to a little bit of nitty-gritty. So, for starters, right, we're going to denote the ring of symmetric functions. Just going to denote that by sim. And it has several generators that we like. Namely, we have the power sum symmetric functions. We have the elementary symmetric functions. And then we have the complete symmetric functions. And then, of course, my favorite, we have the Schur functions. Right, we're here, lambda is a partition. So it's important to note that these are generators over Q, whereas these are generators over Z, right? And our intent is to categorify some things, so it's important to note that we're working over integers, as we'll see later on. Now, sim has a well-known inner product, known as the Hall inner product, which tells us that two Schur functions are orthonormal. Right, where mu and lambda are just partitions. And with respect to this inner product, we can define certain operators, namely the adjoints with respect to multiplication. Right, so we can define F perp, so sorry, let me say this. Given an F in sim, there's an action of F of the ring of symmetric functions on itself by just acting by multiplication, right? And then we can define F perp as an element in the endomorphism of Zim, where F perp of U, V is defined in the following way. So it's the unique function that satisfies this, right? Where this inner product is precisely this Hall inner product. So that means that we can define the adjoint versions of all these, right? So essentially we have Pn perp, En perp, Hn perp, et cetera, all living here. Cool. And so one of the things that we might want to consider is what happens when we have the action of both of these. You know, for example, oh yeah, sure. Oh, maybe I'll just act. Is it better to, well, I'll continue here and then move back. So for example, we have Pn and Pn perp both acting on the ring of symmetric functions. We might ask, well, what is their commutator? So here we have that this is nothing more than n times the Kronecker delta function, right? So they're either 0 or, sorry, one of these should obviously be m. Let's make this one an m. It's either 0 or n whenever n and m are equal. So what that actually gives us is the fact that the Heisenberg algebra actually acts on sim. The reason being that the Heisenberg algebra, the infinite dimensional Heisenberg algebra in this case that we're considering, is generated by two sets of elements, you know, Pn and Pn perp, alpha, alpha n perp, whatever you want to call them, that satisfy this commutation relation. Great. But I told you that Pn and Pn perp, right, are generators over Q. And we would like some sort of integrality here, right? Because remember that if we look back at our big picture, we have an action of the Heisenberg algebra, but we want to categorify this. So we really are looking for integral things. So, well, the Heisenberg algebra also has integral generators, right? In the same way that the ring of symmetric functions does. In particular, we have that H has generators over Z, given by, let's denote them, Pn and Qn. And these generators satisfy modulo the following relations, right? That if you multiply them, then the Pn's commute. So that one's easy. And it tells you how to move the Q's past the P's, right? So Pn, and if you want to move a Q past an P, then we get that this is the sum over Pn minus K, Qn minus K. Right? So if you're familiar with partitions, this will start looking really similar to multiplication of symmetric functions, as it should, right? Excellent. So what does that tell us? Well, in particular, this gives us that Pn acts on sim by multiplying by really just your elementary symmetric function, right? And Qn is really just acting as multiplication by its adjoint, right? And that's exactly what these relations are encoding, right? So that's why I mentioned if you're familiar with multiplication of symmetric functions, then these relations will look really, really familiar. So you might ask, all right, we know what the alphas are, sorry, we know what the p's are, we know what the h's are, there should be an analog for the e's, and of course there is. So there's an alternate set of generators, which we're going to denote by p to the 1n and q to the 1n, right? And again, you'll start noticing that here, the n and the 1n are looking suspiciously like column and row partitions. And that's because they kind of are. and then modulo analogous relations. Okay, so we have this entire set of bases, or generating sets. Why do we care? Well, because there's a lot of really interesting relations between the different generating sets that are going to be the basis of the construction for this boson-fermion correspondence. In particular, we have relations of the form like, let me get it right. Yeah. So we have relations, for example, like this, that if you take a sum of hm, z to the m, then you end up that this is equal to, for example, the exponential of the sum. Sorry, this is a bit lengthy, but I'm making a point, I promise. Pn z to the n over n. Right? And so if you're familiar with vertex operators at all, then you'll realize that these are kind of the building blocks, right? Essentially, once you start accumulating things, expressions of this form and multiplying them, that's exactly how you get them. So this is where we start seeing these VOA showing up. Right? So one of the things that we could do is precisely construct more operators based on these. Any questions before I stop? I realize I haven't. All right, great. Cool. So we have these so-called Bernstein operators. And what are they? Well, so given any A and Z, we're going to define our Bernstein operators, let's call them BA, to be the following sum. So it's an alternating sum, H, and this is an M, e to the m perp, right? So these are these symmetric functions that we were discussing before, and they're adjoints, and you're summing over n minus m equal to a. And then you have some sort of adjoint operator, which is defined almost analogously. That should be an m. Yeah. Almost analogously by just reversing what you're doing here. And then here you're summing over m minus n equal to a. Cool. So why do these operators, why do we care about them? Why do they show up? Well, it turns out that these operators show up a lot in the theory of symmetric functions for many, many, many reasons. In particular, we have the following theorem due to Zelevinsky, which tells us that the Bernstein operators act like annihilation and creation operators for Schur functions. So what that's saying is that if we take a partition, say lambda 1 bigger than lambda 2, lambda n, some arbitrary partition, then if we act, let me get the order straight, yeah, lambda 1, b, lambda n on 1, you actually construct the Schur function. So this is telling us they act like creation operators. And analogously, the adjoints act like annihilation operators, right? So if we start to do the opposite direction, b lambda n, lambda 1 star of s lambda, then you recover just 1. Moreover, these operators satisfy pretty interesting commutation relations, right? So they satisfy the following commutation relations. Namely, we have that BA minus 1, BB plus BB minus 1, BA equals 0. We have that BA plus 1 star, BB star, that this is also equal to 0. And we have something telling us how to commute the BAs plus times the BA stars. Then we'll start here. B. This again is 0 if A is not equal to B and 1 if A equals B. Right, so we have these commutation or anti-commutation relations rather. And if you're familiar at all with Clifford algebra, so you've seen them before, you'll notice that these relations are surprisingly or remarkably very Clifford-like, which is where you start seeing this Clifford algebra that I told you would show up eventually. But they're not quite Clifford algebra relations. Right here, the A and here you have A minus 1, you have an A, you have a B minus 1, you have a B, so they're somehow shifted. But they, as you would expect, they will play a pretty crucial role. Okay, so here's the basic setup. What do we want to do? Well, we want to categorify this, right? So we're going to start, first of all, by categorifying the ring of symmetric functions. That one's easy. In particular, this is very old work. Wow. So everybody seems to cite Heisenberg. It might be older than this, but I guess this is the first time it showed up written, which is basically just the statement that if you take K0 of CSN modules, the category of CSN modules, then this is isomorphic via the Frobenius character map to precisely a ring of symmetric functions. Great. And what this is really doing is just saying, all right, let me send S lambda, our spec module. So to, if you take the Frobenius character map, you get your Schur function on this side. Right? Moreover, through this map, what we're doing is we're not only categorifying the objects, we're also recovering, obviously, the algebra structure. In particular, you have that induction and restriction get sent to, here's the algebra, and this gets sent to the coalgebra structure on the ring of symmetric functions. So you're really getting a very nice description of everything. Okay, so I said this part was easy. So that gives us sim. What else do we need to categorify? Well, we would like to categorify the Heisenberg algebra. And at this point today, there are so many categorifications of the Heisenberg algebra. But what we are going to focus on here is the very first one. So this is due to Kavanagh, of course. So so Kavanagh defined a Heisenberg category in the following way. So first of all, he defined the objects to be generated by P, which we're going to denote by an upward arrow, a Q, which we're going to denote by a downward arrow, and whose morphisms are going to be planar diagrams generated by a crossing, a cap. We have a cup. We get all the directions straight. Modulo the following relations. So we have this is going to be equal to just this. So this is telling us if you do a crossing twice, as long as the strands are pointing in the right direction, they're just going to undo themselves. We get this one. And then we get a few others. Plus, also, we get the following relations, which are telling us, well, what if we have something like this? Well, this doesn't just undo itself. If we have down and then up, what we actually get is down and up minus this. We get this. We get that the right criss curl is 0. And we get that a bubble pointing counterclockwise is just 1. So essentially, if you ever see a diagram that has a bubble pointed like this, you can essentially just erase it. Great. What is this category? Well, this category is monoidal, it's idempotent complete, and therefore it suffices to explain what the relations are just for P and Q. So in particular, we have the following two relations, this one and this one, right? And what that tells us is that we have an action. Should I?
Is P equal to Q?
Yes. Yes, yes. Should I swap the boards? Is it better if I move them, move one up and one down, maybe? I don't know. Here. So moves things up. Okay. Yeah, so in particular, we have that the relations just for the upward pointing arrows tell us the following. They say that we have an action of CSN on basically any combination of upward pointing strands, right? So if this is just denoting the concatenation of n upward pointing strands, so P tends to do with itself n times, and this is just telling us the group algebra for the symmetric group acts on it, right? Because we have that a transposition squares to itself, that's what the crossing really is kind of encoding, and then here we just get relations for transpositions that are close, right? Cool, and then obviously also for Q tends to with itself n times, right? You just make all the arrows downward pointing. So in particular, what this tells us is that we can consider the images of Young idempotents. In H, right? So that means that for any partition lambda, we have some object P lambda, maybe I won't put P lambda, in H that is an idempotent. So we can consider some special examples of this, namely, if we have lambda is just a row, right? So something like this, just a row partition, let's call it with n boxes, then if we consider En, which is the complete symmetrizer on n strands or on n elements, right? So this is just the sum over every element in Sn. Then what we get is that 1 over n factorial. That the image of this, we're going to note it by Pn. Here n is denoting a partition, and this is just going to be precisely each permutation can be expressed in terms of crossings, and it's going to be the sum over every such crossing normalized by n factorial, right? So we're going to denote that by a white box on n strands. And likewise, we can consider what if lambda is a column, right? And then in that case, we get precisely that the complete anti-symmetrizer, call it like this, or maybe, say that again? So remember that our category is idempotent complete. So what we're really just considering are, these are just objects in our category, yeah? Yeah, so you define it like this, and then formally you take the Caribbean envelope afterwards, but yeah. And so what this means, oh, where was I? Oh yeah, so we can take the complete anti-symmetrizer, which is 1 over n factorial. We get minus 1 to the degree of, no, sorry, minus 1 to the degree of sigma times sigma over the sum over every possible permutation, right? And again, you get some object here, which we're going to denote by a black box or a shaded box with an upward pointing strands, right? And obviously, this all holds for Q as well. So, for example, right, just so to make sure that we're all on the same page, if you take n equals to 2, then the complete symmetrizer, E2, is just 1/2 times the partition, the identity, plus the permutation that sends 1 to 2, right? And diagrammatically, that's just saying, well, we're going to take 1/2 times the identity plus a crossing. And this is exactly what P2 is, right? And analogously, if you take the complete anti-symmetrizer, so E12, you get 1/2 times the identity, but now it's minus this. And then analogously, you would get 1/2 times this minus a crossing, right? And this is P12. And then denoting it like this is just shorthand. So pretty straightforward. Great. And then what else can we categorify? Well, in our big picture over here, right, we said that the Heisenberg algebra is actually acting on the ring of symmetric functions, right? So we have a categorification for the Heisenberg algebra, namely Kovanov's Heisenberg category, but I need to tell you how is this acting on the group algebra of the symmetric group, which I wrote somewhere categorified what I wanted, yeah, up there, right? That categorifies the group algebra or the ring of symmetric functions. So the action, H, acts on CSN modules by induction and restriction. So in the following way. So namely, we have that P acts by induction. So how do I want to write this? Yeah, so we have induction. So P, we can think of it as saying, all right, we're going to start with an Sn module, and we're going to induce up to an Sn plus 1 module, right? So this is a map that is going from CSN mod to CSN plus 1 mod. And then in the same way, Q, and this answers your question about whether they're by a joint, we have that restriction. Q acts by restriction. So here we have n, and it's going to just bring us down to an n minus 1 module, right? So CSN mod into CSN minus 1 mod. So diagrammatically, this is really just saying, if we have some sort of diagram and we want to consider what is the action of this on some sort of Sn module, it's really just label the rightmost region, and either things are going to be 0, things are not going to be 0, but you're going to know what you end up at the end, right? By just basically counting what the labeling on each of the regions is. Cool. So this is obvious, but I'm going to point it out just because it's important. Clearly, if we act on the trivial module, then Q, I don't know why that's a Q. Q is going to act by 0. And we have that P lambda. So if lambda is any partition and we act on 1, we can induce up. This is, we can say that that's isomorphic to the spec module. Awesome. Okay. And then, where do I want to put this? I guess I need to erase something. Oh dear. That one might be gone forever. So where was I? Oh, yes. So this Heisenberg category, I mean, how do we know that it actually categorifies the Heisenberg algebra that we're after? Well, that's a theorem. And this is due to Kavanov and very recently by Brundon, Savage, and Webster, as in like last month recent, that we know that the Heisenberg algebra is in fact isomorphic to the Grothendieck group of this category. So for a long time, it was only known that it was injective, or sorry, that this was injective into this. Cool. Awesome. So I erased it, but remember that in the big picture, right, we had these Bernstein operators also that we want to categorify now. So how do they fit into this? Well, so we want to categorify our Bernstein ops. Right? How do we do that? Well, so the idea is the following. Namely, if you have sums, so those are easy to categorify. Those categorify to a direct sum. If you have a difference, that's also not too bad. Differences categorify to homological grading shifts, so homological shift. And what this is telling us is then that if we have an alternating sum, right, remember that the Bernstein operators are alternating sums of these symmetric functions and their adjoints, then an alternating sum is necessarily going to have to categorify as a chain complex. So what that means is that for us, if we're going to want to categorify the Bernstein operators, we can no longer work in just Kovanov's Heisenberg category. We have to pass to the homotopy category, right? So this is exactly what Tony was mentioning earlier today. So we need to pass to, so he denoted it com, but I use different notation, so to the homotopy category. Category of H, namely this, which in Tony's notation is just this. They're the same thing, right? So, okay, I just want to, for continuity, right? So these are chain complexes where the chain maps are, well, the morphisms are chain maps up to homotopy, right? So null homotopies are modulo null homotopies. Awesome. Okay, so what are Bernstein operators? Well, we had, remember, at BA, what was this? This was an alternating sum of -1 to the n Hn Em perp, right? N minus m equals a. So we know what the Em perp categorifies to, do we? Does anyone remember, or can they deduce it? Well, what do we have? We have that the p's up there are acting by induction, and they basically, if what we said here was true, that the p lambdas correspond to our spec modules, then if we take lambda to be a row or a column, and then we take the Frobenius character map, what this is telling us is that secretly, this, if we wanted to categorify it, is just Pn. In our, where this is in H. All right, so this is an upward strand tensored n times with this white box symmetrizer, right? And then this Em perp is precisely going to be Qm 1 to the m, right? Because it's an anti-symmetrizer. And so this is actually precisely going to be an M, a shaded box, if you want to think about it diagrammatically, but now the arrows are going to be pointing downward. It's a lot of effort erasing the board. Wow. Okay, so categorically, then that means that our chain complexes, we define the categorical Bernstein operators as follows. We have that BA, right? And I'm sorry for the notation. Imagine this is like Math Cal or Math Proc or something different from that one. So here we're working in the homotopy category of Kovanov's Heisenberg category. So this is defined to be the following chain complex. Namely, we take P A plus N, right? Again, this is a P in Kovanov's Heisenberg category. We take Q, 1N into P A N minus 1, Q 1N minus 1, and so on, right? And so on here, where the differential is taken to be the following map. right? So this is one strand, so this is a white box, this is a black box, and then you take the remaining strands upward and downward. Right, because you could say, well, why would we want to categorify this if we're really just going to do something stupid like lift the objects to, or lift the symmetric functions to objects in our category that kind of have the exact same commutation relations. We're not really doing anything interesting. And really, it's the fact that we can put a non-trivial differential on there that makes things a bit more exciting, right? And then in the same way, we can define, I wish I could, oh, sorry, yes.
In your sum, is it n times m is equal a or n plus m?
In the sum, it's n minus m equal to a. It's the difference. N minus m equal to a. Yes, that's the difference. Yeah, so that's why n minus this is equal to a. Yeah, yeah, yeah. Right, and so then we have the dual, which is exactly just going to be the adjoint to this, right? So we swap every partition essentially for its transpose, right? So we're going to have 1 to the a plus n. We have q to the n. And then we can imagine that we're really just taking the chain complex and kind of rotating it and then changing the direction of the arrows. So here we'd get a p, 1 to the a plus n plus 1. So now the differential goes up by 1, and a q to the n plus 1, and so on, right? And so you'll notice that I didn't put bounds on this. And the reason for that is that that sum is infinite, right? So what that's telling us is that these chain complexes, they are not finite chain complexes, they're infinite. But obviously, Q, a partition can only have, does it only make sense if this number is positive, right? So eventually, this is going to be 0 here, right? Eventually, your chain groups are going to die. So the BA is going to be bounded below. So this lives in, it's denoted by K minus of H. Whereas it's dual, right? And like I said, this is why it's easy to imagine this is basically just kind of taking the chain complex and rotating it. This is going to be bounded above instead, right? Because eventually the ends will be 0. Or depending on the value of A, the p's might be 0. So this is going to be bounded above. We're going to denote that by K plus of H. Cool. So what properties do these categorical Bernstein operators, and I swear they do matter to the big story. So what properties do these operators satisfy? Well, so we have the following theorems. Namely, first we have that the Bernstein operators, or sorry, the categorical Bernstein operators act like creation and annihilation functors for spec modules, right? So what that's saying is that if we take a partition, Bn, and we take the tensor product of these chain complexes, B lambda 1, and we act on the trivial module, we recover, right here, this is our spec module. Or rather, let me say it like this. We recover P with the partition lambda 1 through lambda n of 1, right, which is isomorphic to our spec module. And then analogously, if you take the reverse thing, this is just going to be 1. And then, of course, this is really just a categorification of the theorem before due to, wow, what is the name? I'm totally blanking. Zelevinsky, thank you, of course. Thank you. Right, this is just categorifying Zelevinsky's theorem. Right, that our Bernstein operators created and annihilated Schur functions. And secondly, we have these commutation relations, which I guess I erased. They're here in the shadows. These almost Clifford-like relations that the Bernstein operator satisfied. Well, we have categorical analogs of them, right? So we have that the BA satisfy and BA star satisfy categorical, and I'm not going to write them out, but I hopefully will be able to write them at the end, categorical analogs of the anti-commutation relations. And of course, this is always up to homotopy, right? Because we're working in the homotopy category. Cool. So what this is really just telling us is, okay, the categorical Bernstein operators are categorical Bernstein operators, right? They're not really, that's not a misnomer. Cool. So what does this big story have anything to do with bosons, fermions, this correspondence that I told you we were going to categorify? Well, that's the next thing. Before that, does anyone have any questions about this story, right? Heisenberg category, the objects, the Bernstein operators themselves, the chain complexes? Okay. In that case, I'm going to erase. So bosons and fermions, where do they fit into the story? So in order to do that, we need to kind of leave the categorical realm for a second and consider the following. So suppose we have a vector of the form, namely, suppose I give you a sequence of half integers and I order them in such a way that there are only finitely many positive entries missing and finitely many negative entries missing, right? So something like this. And eventually this stabilizes. Right, so you'll notice that here we have a 9 halves missing. Here we have a 5 halves missing. Here we have a 1 half missing. And then here we have a minus 3 halves missing. So if I give you a vector of this form, and I tell you, all right, this is 3, this is 1, I'm just counting the number of negative and positive half integers that are missing, and I take their difference, that's 2, and I call this the charge of V. Then if you take the collection of all such vectors, you take the span of this, so if you take the C-span of vectors of this form, then this is what we're going to denote fermionic Fock space, or as it's commonly known, the semi-infinite wedge or the half-infinite wedge, or the space of semi-infinite monomials. It takes a lot of names. And it turns out that this fermionic Fock space, we denote it by F, you can grade it by charge, right? So let's call it FQ, where Q is an integer, right? Because every vector has an associated charge to it. And on this space, we can define creation and annihilation operators analogous to what the Bernstein operators were doing for the ring of symmetric functions. We do that by defining the following operators. If we take an integer j, then this is going to act on such a sequence, so I2, blah, 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 by 0, oh well, let me not do that one yet, by inserting a vector ij, or an integer ij, in position j, if such a thing is possible. So it's going to be blah, 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 and then is, j minus 1/2, because I'm taking j to be an integer rather than a half integer, is plus 1, if j minus 1 is snuggled between s and s plus 1, or 0 if it's not possible, right? So these is a wedge product, so that's just telling you, all right, if the number is already there, you can't add it, and if it is there, then it's 0, right? And when you add it, just essentially you're appending it to the beginning and then flipping it through, hence the minus 1 to the s. And then analogously, we have the annihilation operator, which is doing exactly the same thing, right? It's going to give me, it's going to take it away if it shows up, or it's going to give me 0 if it was never there to begin with, right? So again, minus 1 to the s plus 1, I1, is minus 1, is plus 1, if j minus 1/2 was equal to is, or 0 else, right? Again, take it away if possible, otherwise not. And it turns out that these two operators on this fermionic Fock space satisfy certain anti-commutation relations. Namely, they satisfy the following. So psi I satisfy the relation psi I psi j plus psi j psi I is equal to 0, and then the same holds for psi I star. And when you commute them, then again, it's 0 if I and j are different. It's 0 if I and j are different, and 1 if I and j are the same. So if you remember the relations that I wrote for the Bernstein operators at the beginning, I pointed out that they were very, very similar to these, right? The only difference being that for the Bernsteins, we didn't have quite I and I. We had something like an A and an A minus 1, and then a B minus 1 and B plus 1 or something. There was some sort of shifting going around. And what we want to do here is relate these to these Bernstein operators, right? Because the fact that these operators satisfy these relations are precisely encoding the fact that the Clifford algebra acts on this fermionic Fock space F, half-infinite wedge, however you want to call it. Right? So how do we relate this, though, to the previous story? Suddenly, we seem to have two tails that have nothing to do with each other, right? One is acting on symmetric functions, the other one's on a semi-infinite wedge. What's the connection? Well, we have the following fact, which is that if we take each graded piece of these, right? So if we just consider the space made of generated or spanned by vectors of this form with some specific charge, pick your favorite charge, it doesn't matter, call it FQ, this is actually isomorphic to the ring of symmetric functions, which means that if we just take a direct sum of infinitely many copies of the ring of symmetric functions, right, with some sort of formal parameter keeping track of what piece we're on, that this is secretly just isomorphic, I guess I'll call it Q, isomorphic to just F, right? Because each of the pieces is isomorphic to each of the graded pieces of this. And in this way, we can relate the two actions, right? Because what we actually have is, on the one hand, we have infinitely many graded pieces of the ring of symmetric functions. This is isomorphic to this fermionic Fock space. And what do we have? Well, here, if on each copy of the ring of symmetric functions we have an action of the Heisenberg algebra and we have an action of these Bernstein operators, we certainly have it on all the copies. You know, you just act locally. So here we have an action of H. Here we have an action of this Clifford algebra by these operators that we just defined, which tells us that we can take this Clifford algebra action and just move it over through the isomorphism, and induce an action of the Clifford algebra on the ring of symmetric functions. Right, so we have some sort of induced action of the Clifford algebra here. So that means that essentially we can just kind of forget this entire story and not worry about that categorically. Great, so what is the boson fermion correspondence, right? Well, a priori these two actions have nothing, absolutely nothing to do with each other, except that they do. And the whole point is that they are related through these Bernstein operators. Right, and that is a theorem. Of the following theorem due to Katz, which tells us that the action of CL on sim, or I guess many copies of sim, is realized through the following objects, right? So if we take an object, let's call it t to the c times f, so this is just a symmetric function, and the t to the c is really just there to tell us what graded piece it's on. Then the psi i's act locally in the following way. So this is nothing more than you shift up by 1, so you just increase the charge by 1, and then you act by your Bernstein operator, where A is just I minus C minus 1, right? Remember the Bernstein operators act on symmetric functions. And then the psi I star does essentially the same thing, but it lowers the charge by 1. And of course, it acts by its dual. Cool. So that means that really, if we wanted to categorify this theorem, the key is categorifying the Bernstein operators, because these shifts are really just formal power shifts that categorically don't really add much to the story. And this is exactly the content of the conjecture, right? So like I said at the beginning, I'll say it again. So in 2013, Kaudis and Sussin conjectured a categorification of that theorem. We have 5 minutes. Yeah, sure, we could do this. And I'll just state it right here. So they conjectured it, and it's now obviously a theorem, right? And namely, it says the following, that if we take these Bernstein operators, essentially with some, like I said, formal grading shift, then you have the following relations. So psi I, psi j is isomorphic to the following. So we have psi j psi I with a shift of -1. So this is a homological grading shift. We have psi j psi I with a shift of 1. And this depends on whether I is smaller than j or I is bigger than j. And this, obviously, the same holds for psi I star, right? And that's categorifying that top relation. The fact that you can, commute them modulo a sign, right? Because remember that when you decategorify a homological shift, 1 or -1 really just decategorifies to a minus sign. And then we have the following relation, which is a lot more interesting, which is the second one, which says that psi I, psi j star. So this is homotopic to the following. So it's psi j star psi I with a shift of -1. But rather than I bigger than j, you have I bigger than, or I smaller than j, you have I bigger than j. It's, oh, sorry, and then I forgot, obviously, that psi I squared is 0, right? So this is telling me if my I and j are the same, then psi squares to 0. So it's null homotopic. And then we have psi j psi I with a shift of 1 when I is bigger than j, right? And so this is encoding, again, the second relation when I and j are different. However, when they are the same, you get a much more interesting relation, namely that psi I star forms a distinguished triangle. Not just in one direction, but in the opposite. So this is a distinguished triangle. Now,
I got lost somewhere. Is
yes.
it the same size that appears in both theorems, or is one of them categorified?
Say that again?
Is it the same psi that appears in both Kite's theorem and yours, or is it use the categorification of the previous one? It's a categorification.
Wait, I don't understand. What? Oh, this psi?
Yeah.
No, sorry. Okay, so I skipped a step. Namely,
So you didn't
in order to categorify the psi, it really is just essentially categorifying the Bernstein operators, which are these chain complexes that I spoke about before. Sorry, yes, there's a...
Your psi is just take the same thing, but with categorical.
Yeah. It's basically just take the Bernstein operators, the categorical Bernstein operators, these chain complexes, add some sort of formal, grading shift, categorical formal grading shift, and then that's exactly what these categorical psis are. Exactly. Yeah. That's why I spent so much time on these Bernstein operators. They're exciting, but this is really the punchline. Yeah. So I'm kind of lying here a little bit, because what happens is, I have like 3 minutes, I can talk about this. So what happens is that the first relation, so this holds wonderfully, right? This just holds in, I have no more room. Well, this holds in the full homotopy category, right? As chain complexes. These are homotopy equivalences. Why? Well, remember I mentioned that these psi's and these psi I stars are infinite chain complexes, right? But in particular, if you take a chain complex that's unbounded in one direction, but bounded in above or below, whatever, and you tensor it with a chain complex of the same flavor, then you're going to end up with something that has the same flavor. It's unbounded in one direction, but it's bounded in one of them at least. That allows us to perform homologic algebra that makes sense, nothing too bad, a little bit hairy, but not too bad. However, when you start dealing with chain complexes that are unbounded in opposite directions, right? So the psi I is bounded below and the psi j is bounded above. That tells us that if you take the tensor product of these things, you're going to end up with a chain complex that is completely unbounded, both above and below. And that means that if you're trying to construct certain chain homotopy equivalences, as we do here, you have to be very, very, very careful about finiteness conditions, because some of the things that you might want to do that hold for finite or half finite, semi-finite chain complexes don't hold. So in particular, here, what we actually do to show it is not just fully in the homotopy category, but we assume that we're acting on Fock space, right? So that what this is actually categorifying, this relation, only holds when it's acting on modules over, or SN modules, whereas this really just holds abstractly for chain complexes in and of themselves. Right, and then in the last minute, I want to point out that there's a missing piece that I didn't talk about, right? Namely, here. Right, in this picture, I told you what the Heisenberg algebra was, or I didn't do it, but Kavanagh did, what the Heisenberg category would be. Symmetric functions, that's just modules or SN modules. The Bernstein operators, we know that. The boson-fermion correspondence is really just essentially categorifying these and proving that they satisfy certain commutation relations. But I never talked about what the Clifford category is, right? And that's because that's actually a large part of the motivation behind this project is figuring out, well, if we construct this correspondence, can we actually construct a categorification of the Clifford algebra where the objects would be precisely these chain complexes that we have here? Of course, we have the objects, but then what remains to show, obviously, in order to have an interesting categorification is what are the endomorphisms? Unfortunately, Kavanagh's Heisenberg category is a bit difficult to deal with. And so this is a very non-trivial question that remains open, but there's still some work to be done. Yeah, thank you.
Other questions?
Yeah.
And the principal embedding of the Heisenberg category into, let's say, SL infinity, what do the Bernstein operators get sent to? Is it
What do the Bernstein operators get sent to?
To Ricard complexes in some way?
Oh. I don't know what these particular, yeah, I don't know. I've never actually considered it for these specific ones. That's a good question.
Even at the categorified level, can you realize Bernstein operators as and the principal level?
I don't know. Probably. I mean, there is definitely, so the Bernstein, this boson fermion correspondence, really, you have kind of three pieces, right? You have the Clifford algebra, you have the Heisenberg algebra, and then you have affine SL infinity. And you kind of have boson fermion correspondences for each of them, right? And so potentially, if here you have the Bernstein operators, there should be analogs that spread everywhere, and they're all in these infinite sums that show up as vertex operators. But specifically for this case, what their image is, I don't actually know. Yeah.
If psi I is psi I plus 1 star, that's like a Chevrolet generator or something.
Is it just as that obvious? Oh, okay. Good. I learned something. Cool.
Well, then, thanks again.
Thank you.